Hi everyone. So today let's solve the this one. Not solve the basically. Let's discuss on the topic this one square root decomposition on the trees algorithm. Right. So previously what did we do? We discussed on the topic Euler-2 technique algorithm. That was easy, right? So now let's discuss on the topic square root decomposition on the trees algorithm. So this is very important. And one more thing. So this is going to be the last algorithm within the tree-based algorithms playlist, right? So let's finish it off with this particular algo, right? Square root decomposition on the trees. Let's get into the definition part. So what does the definition part say here? Square root decomposition on trees is an optimization technique. Mainly, it is an optimization technique, right? So this algorithm mainly it is used for the optimization purpose. It is used to answer the queries like path sums, again, path sums, subtree queries, or the ancestor queries efficiently on the tree, right? So again, let me read this one again loud. Just listen to this carefully, man. Square root decomposition on the trees is an optimization technique. It is used to answer the queries like path sums, subtree queries, or the ancestor queries efficiently on the tree, right? So what it does, it divides the tree into blocks. It divides the tree into blocks of roughly square root of n size, and it processes queries in this one big of square root of n, or the big of square root of n logarithmic n time instead of the big of n. The main reason that we'll be going with this one square root decomposition technique is because uh, due to the optimization purpose itself, right? So because we can just solve the this one problem within the big of square root of n or big of square root of n logarithmic n time. So that is the biggest advantage, huge advantage basically, right? So that is the reason we'll be making use of the square root decomposition mainly, the technique, right? Hope this is fine. Next, let's move on with the explanation part, right? In a normal array, square root decomposition breaks the array into blocks of size, right? Suppose when we consider the normal array, square root decomposition, it breaks the array into the blocks of size square root of n just to process the range queries efficiently, right? Similarly, in trees, we can decompose nodes. When we are considering the trees, what we can do? So usually we decompose, right? So here, when we consider the array, it can break the array into the blocks of size, right? What happens when we are considering this one trees? Similarly, in trees we can decompose. Usually for breaking into the blocks, we make use of this one. We will go with the decomposition itself, right? In the trees. So similarly, in trees we can decompose nodes into heavy paths or blocks based on the traversal order, like Euler tour. So why did I mention this one? Previously we had discussed on the Euler this one Euler-2 technique algorithm. This is the reason. So I hope that algorithm is completely clear, man. That algorithm is linked with this one. When this one, what decomposition purpose, right? So this one you have to know. This is very important. These three algorithms based on the decomposition, right? We will be making use of it with this one, usually segment tree or the Fenwick tree, right? Segment tree or the BIT or binary index tree, right? So it's heavy light decomposition, Euler-2 technique algorithm, as well as the square root decomposition. So these three helps us a lot in the optimization, especially if you're giving, especially if you're doing CP, right? Competitive coding, especially if you're giving the contests in this one, what do we call, Codeforces, Codechef, and Etcoder, right? Maybe others as well, but I do give this one contest within this one. What do you call? These three basically, right? So especially if you're doing CP, these kind of algorithms are very handy. You never know when you will be using it, right? So usually there are n number of problems that will be asked, that will be based on the that will be solvable by segment tree and the Fenwick tree. At that point of time, for the optimization purpose, we will be making use of this one, heavy light decomposition or the Euler-2 technique, or sometimes we can go with a square root decomposition on tree as well. So we will be asked many problems that is based on the trees, right? So during the DP on trees, during the this one, when we solved the this one problems, um, this one that were solvable by the DP, right? Usually by the DP, I mean DP on the trees. So we have seen, so we have went with certain algorithms, right? We have seen the centroid decomposition there, right? So along with this one as well. what do we call, we have seen the heavy light decomposition along with the square root decomposition as well while solving the DP on trees problems, if you remember, right? So we have come to the topic graphs now. So we are solving the problems on graphs now. If you remember, there we have made use of the heavy light decomposition, centroid decomposition. These algorithms we have made use of, right? So now in the graph, I am solving this one, centroid based problems, right? If this one, right? So this is fine. Now, again, let's move on with the further things. So here, similarly in trees, we can decompose the nodes into heavy paths or the blocks based on the traversal order, like the Euler tour, right? Right. Next, each block has around square root of n nodes, and we store the pre-computed computation, this one, computation or the information, right? Like sum or minimum for those blocks, for those blocks. When a query is made, for example, let's consider find sum of values from node U to node V. We are just considering this one as the example. Right. Suppose if you want to find the sum of values from the node U to node V, we jump block by block instead of traversing every single node, right? So this, what it does, it reduces the query time for the large trees. It reduces the query time for large trees. Let's try to implement the same thing in the form of code or the algorithm, right? Let's see the same. Right. So let's do one thing. Yep. Now let's start writing the algo. Right. So just give me a second here. First, so we'll be making use of certain this thing. What do we call math operation? So let me import math here. So I'll just go with import math, right? So also from collections, let me import the. So we'll be making use of the default dict as well. So I'll be going with import default dict, right? So this is fine. Now the first step is we have to create the tree as the adjacency list, right? We have to create the tree as the adjacency list. So I'll just go with tree equals. Let me make use of the default dict here. So I'll pass the list. I'll pass the list. Simple, right? So now let's consider the edges. So let me consider the easy one, man. I don't want to consider the this one. What do we call difficult one? I'll just go with 1, 2. So this one 1, 3. I'll just go with 2, 4. This is fine. Let me go with 2, 5 as well. Let me go with 3, 6 as well as let me go with 3, 7. 3, 7. This is fine. Now, yeah, I'll just come here. Let me this one. Yeah, so this one will be 1. This is fine. Let me go with 2. Let me go with 3. So I'm just showing the build basically, whatever we have considered it just here, right? So 1, 1 to 2, 1 to 3, and 2 to 4 and 5 I have considered, right? So 2 to 4 and 5, and finally 3 to 6 and 7. 3 to 6 and 7. Let's go from the this one, pure basics, right? So this is the thing that I've considered here, edges, right? So let me delete this one. This is just for the information purpose, right? So now let's move on with the further things. Now let me go with the iteration. So for u comma v n edges, so I'll just go with, we are considering the adjacency list itself, right? So we're just creating the tree as the adjacency list itself. So obviously we have to go with a for loop. Then tree of u normal, what we need to append here, v. From x to y it goes adjacency list, right? So from 1 to 2, from 1 to 3, from 2 to 4, that's the adjacency list. So this is fine. Now tree of same thing, tree of v dot append of, this time it is u. This is fine. Now we are done with the first step. We have successfully created the tree as the adjacency list. Now let's do one thing. Let's initialize the arrays, right? So n we have from 1 to 7. If you see correctly here, this one vertices or the vertex, we have 1, 2, 3, 4, 5, 6, 7, right? So n we need to consider 7 here. This is fine. Now let's go with the values, man. Values equals, so this will be 0, 3. I'll just go with 2, 1, 10, 5. This is just the example, man. You can just give anything. So values we are considering for the this one vertex, particular vertex, right? So this one will be 5, 7. Let me consider one more 6, as I had already left the space. This is fine. Values. Now let's go with a Euler tour to linearize the tree basically. I'll just go with Euler here. Let me assign this one to the empty array. I'll just go with in time here. Let me assign this one to the 0 into n plus 1. We're just making this one as, considering this one as one index basically. So I'll just go with out time, in time and out time we are considering. So this one will be one indexed as well. So this one will be 0 into n plus 1. Fine, simple one. Now we are done with the second step, man. Let's go step by step clearly, right? Clearly and also concise, right? So third step is let's perform the DFS, or let's go with the DFS just to get the Euler tour order, right? Just to get the Euler tour order. So this is the reason we need to know the Euler tour technique. The previous one which we had discussed, the algorithm Euler tour technique. So see, it will be very helpful within the square root decomposition on the trees as well, right? So now let's go with the DFS node comma parent here. This is fine. Now let me go with in time here. In time of node, let me assign this one to the length of, let me give here Euler. This is fine. Let me go with Euler dot append of this one node, right? So I'll just go with for, we consider individual child in the tree nodes basically, right? So I can just represent in this way, tree of node within the array, right? So within the for loop, what if child not equal to parent? Yep, what if the child is not equal to parent? Then we have to recurse, right? DFS of, we have to pass child comma node here. This is fine. The final step would be, let me go with the out time. So it is showing out time. Yeah, out time of node. Let me assign this one to length of the Euler, right? Euler minus 1, right? So this is fine, man. Finally, we'll start the DFS from the root, nothing but 1, right? So DFS from 1 also, let me mention here minus 1, right? So this is fine. We are done with the DFS basically. We can just make use of it later, right? So this is fine. We have already done, right? So we are starting the DFS from the root one, sorry. So next, let's move on with the further steps here. So the step 4 is we will be creating an array based on Euler order of the nodes, right? Again, let me tell you this one again, just listen to this carefully. We are creating an array that is based on the Euler order of nodes, right? So array equals, so I can just write it in this way. Let me go with the values here, values of the node for this one, node in Euler, this one. Fine. Next, this was the fourth step basically, right? Yeah, this is the fourth step, sorry. Next, let's move on with the fifth step, nothing but we will be building this one, square root decomposition, right? So the algorithm name itself is the square root decomposition on the trees, right? So now let's come to the main part. Let's build the square root decomposition. Let me consider here block size. So this one will be int math dot square root here, right? So let me go with length of, let me pass the array, right? So this is fine, I believe. Next, let me consider number of blocks. I'll just go with num blocks, man, here. This is fine. So again, so this one will be length of array, fine, plus let me go with a block size minus 1, yeah, divided by or by block size. So this one block size, yep. Now let me go with a block size here. This is fine. Sorry, not the block size. So we have to go with the sum, right? So let me name this one block sum or sum. Let me go with the block sum itself. This is fine. So this will be 0 into num blocks, number of blocks, or we have considered num blocks itself, variable name. Previous line, line number 50. Yep. Now we are done with this part, man. Now let's move on with the iteration part as usual. So I'll just go with for I comma value in. Let me make use of the enumerate here of array. So I'll just give here block size or block sum, right? Sorry, block sum. So this one will be I by block size. Block size equals block sum of I by block size plus value, right? So I'll just go with a val here, right? Simple. Yep. Next, let's move on with the sixth step. Now we'll be making use of the function, or we'll be going with a function to query the subtree sum using the square root decomposition, right? That also we need to do. So for that one, let's go with a let's write the function query man, or let me go with something like name a query subtree sum. Yeah, def this one query subtree sum. This is fine. Let me pass the node here. Yep. Now within this, let me go with L equals. So I'll just go with the in time here. In time of node. This is fine. The next step would be R equals out time. This is fine of node. Yep. Now let me assign total equals 0. This is also fine. Let me go with while loop while L less than or equal to R. This is fine. Within the while loop, what we will be doing, if L is at the block, if L is at the block start and block fits fully in range, then we have to go with total equals total plus block sum, right? Block sum of L by block size. So let's see the same. Let's write that one in the form of code. You'll understand this one better. So this one will be L modulo this one. Let me go with the block size. If it is equal to 0, as per the discussion, and L plus this one will be block size minus 1 if it is less than or equal to, right, or the R. Then as I've said, we'll be going with total equals total plus block sum. So this one, let me go with the block sum here. This one will be L by block size. L by block size. Finally, we'll be going with L equals L plus block size, right? So this is fine, man. Else, I'll just go with total equals total plus array of L, right? Array of left or L. So finally, we'll go with L equals L plus 1. What we are doing here, basically, we are writing the function just to query the subtree sum using the square root decomposition. This one we have already written. One second. Yeah, this is fine. Let's continue with this one. Yeah, this is fine. One second. Yeah, I meant to say that we have already built, we have already successfully built the square root decomposition, right? So this is fine. We have given L equals L plus 1. Finally, we'll return the total. We'll return the total. So I'll just come here. Let me return total here. This is fine. Let me come out of this one entirely. Now let's move on with the seventh step, nothing but we have to write the function to update the nodes value. So we have to, suppose if we want to update the nodes value, we have to write the function for that as well, right? So I'll just go with the update node here. So this one will be update node comma, let me consider new value as the parameter, right? So here index, let me assign this one to in time. Where is in time? Yeah, in time of node. This is fine. Let me go with a block index here. So this one I'll just go with block index. This one will be indexed by block size, right? So this is fine, man. So the next step, we need the difference as well. For the difference, I'll consider diff keyword. This one variable name new underscore value, new value minus array of index hyphen array of index, right? So sorry, this is fine, man. Now let me go with array of index. So this one equivalent to the new value. Yep. Yeah. This is fine, man. This is fine. So this one will be block sum. This is also fine. Block index. So let me go with the block index. Plus difference. Fine. Block sum of block index equals block sum of block index plus difference. Yep, we are done with the this one function, update node function. We are just writing. We have just successfully written the function to update the nodes value. So this is it for the algorithm, man. So this is it for the algorithm. Little bit lengthier, but it's worth learning, right? So it'll be very helpful during the optimization. So basically, when you're giving the contests or the so in interviews, these kind of questions will not be asked. These kind of difficult questions will not be asked, in my opinion, right? So they'll not ask that much of this one, whatever the company it may be. They'll not ask for that much of optimization, right? So usually for you, it will be asked like to solve the problems in big of n or something like that. Usually will not be going with this much of optimization. In interviews, it will not be asked, in my opinion. If our luck is bad, then we can't do anything, right? This is fine. Yep. Now, let's go with the example usage, or let's consider the example queries first. So I'll just go with a print here, just for the interactive purpose. So let me give subtree sum of node 2. This is fine. And I'll just go with a query subtree sum here. Let me pass 2. So node 2 we have considered, right? So let me copy the same thing here. Let me paste it over here. So I'll go with a, instead of 2, let me make this one 3. Here also, instead of 2, let me make this one 3. This is fine. Yeah. Now, let's update something. We have written the function to update the nodes value as well, right? So I'll just go with the update. Sorry, what did I give here? Hey, what happened here? I did something, man. I don't know. This one again instead. So I'll just give you 3 instead, right? So now let me go with the update node of 5, 20, right? So I'll just go with the print. So this one, after updating node 5 to 20, let me consider 5 to 20. So this is fine. Yep. Let me go with the print. So this one subtree sum of node 2. This is fine. 2, right? So this one will be query subtree sum. This one, yeah, query subtree sum of 2, right? So this is it for the this one algo as well as the example usage, right? So let me do one thing. Let me explain this one before running the code, right? So first, what we are doing, we are creating a tree here, right? So in the line number 26, we are creating a tree using the adjacency list, right? Then what we are doing after this one, after creating the tree using the adjacency list, then we are performing a DFS to record each node's in time and out time in the Euler tour by making use of the Euler tour or in an Euler tour, right? So this is fine. Next, we are building the linear array, right? So we are building the linear array, right? So we are building the linear array, nothing but the array, where it is the line number 47 array, this one from the Euler tour. This what it does, whatever the array that we have made use of, this lets us represent the subtrees as continuous array ranges. Just remember this one, this is very important. Then we are dividing this particular array square root of n, this one n size blocks, and then we are computing the block sum for each block sum for each block. That's what we are doing. Now we are going with a query subtree sum of node. Then we are going with a query subtree sum of node, which efficiently adds block sums for the full blocks and individual elements otherwise. Then finally, we are going with the update node function. What it does, it modifies the node's value and updates the corresponding block sum, right? So example queries, whatever we have made use of, this basically shows how we compute and update the subtree sums efficiently. Let's try running the code. We'll understand the output part as well, right? So let me come here. So yeah, let me copy this one entirely. So let me give Control J here. Yep. So what happened to this one? Let me minimize this one. Sorry. Yeah, 1 second. Clear screen. So let me give Python file name dot py. Right. Subtree sum of node 2, we are getting 17. right? So subtree sum of this one, 2 basically. So let me draw this one. I have already drawn this one. So this one we are considering when here values, right? So here this one we are considering, right? So I'll just 1 second, just give me a second here. We have a lot of time. We can just learn this one, right? So done anything. So this is fine. We have 1, 2, 3, 4, 5, as well as 6 and 7. So the value of this one, 2 is 0. The value of 1, 3. So this one is fine. Let's consider this one later. For the subtree 2, it contains this one. What do we call? Node 2, 4, and 5. For the subtree 2, it contains the node 2, 4, 5. So you can clearly see here, right? It consists of the node 2, 4, 5. Node 2, 4, 5 consists of the values 2, 10, and 5. See here, this is 0, this is 1, this is the value actually. This is 3, 4, 5, 6, and 7, right? Indexing start from the 0, right? So this is fine. This one, second index consists of, we have to consider 2, 4, 5, right? 2 consists of this one value 2, and 4 consists of the value 10, and 5 consists of the value 5. So this one will be 2 plus 10 plus 5 basically, right? So 2 plus 10 plus 5, this is 17, right? So this has to be 17. Right. So subtree 2 contains nodes 2, 4, 5. Basically the values 2, 4, and 5. It consists of the values 2, 4, and 5. When we sum up, we have to get the value 17. Right. That's what we have got here. Subtree sum of some node, the subtree sum of node 2, 17. Right. Next, we are going with a subtree sum of node 3. Right. Subtree sum of the node 3 consists of 3, 6, and 7. Right. Subtree sum of the subtree 3 contains node 3, 6, and 7. Subtree 3, this one consists of the nodes 3, 6, and 7. So when we sum up this one, it will be 3 plus 6 plus 7. Basically 7 plus 6, 13. 13 plus 3 here, 16. Right. So here for this one, we have got 17. And for this one, we have to get, sorry. Oh, we have to consider the values, right? Sorry. I'm extremely sorry. Yeah, value at 367. Value at the 3, we have 1. Index 3, we have 1. Value at the 6, we have 7. 1 plus 7 is 8. And finally, value at the 7, right? Value at the 7, we have 6. So here 6 plus 7 is 13. 13 minus, why minus here? Plus I need to consider, right? Sorry. Yeah, this is 1 plus 7 plus this one, 6. Basically 7 plus 7. Yeah, this leads to 14. Right, so this is fine. This leads to 17, and this leads to 14. Right, so here we have got the output 14. Right, so this is fine, I believe. Now the next part is we have updated the node 5 to 20. See here, we have updated the node 5, this one, the value to 20, from 5 to 20. Right, so from 5 to 20. Now we are considering the subtree sum of nodes. So I have somewhere I have given this one, I have misspelled subtree, I'll change that one. Don't worry. So this one will be subtree sum of node 2. Node 2, again, this is 2, 4, 5. This one, right? 2, 4, 5. 2 and 4, the value remains same. uh, 2 and 10. We have considered this one. What do we call? 5, what we have done, we have what do we call? We have changed this value from 5 to 20, right? So we have updated the value from 5 to 20, right? So that's what we have done. See here, after updating node 5 to 20, so instead of 5 here, we will be going with a value 20. We have updated the index, this one, what do we call, index 5 value from 5 to 20. So this becomes 10 plus 20, 30, 32, right? So we have got the output 32 here. So we have got the output 17, 14. After updating the index 5 value from 5 to 20, we are getting 32, right? The same thing we are considering here. This one, subtree 2 and subtree 3, right? So we have got 32. So we have got the desired output, right? So we have got the correct output here. Absolute correct output here, right? So the algorithm, whatever we have written, works flawlessly here, right? So it works flawless here, means completely correct, right? So now this is it for the square root decomposition on the trees algorithm. And also this is going to be the last, this one, last algorithm in the tree-based algorithms list. Also, so we have hit the milestone that we have completed 50 algorithms. You can clearly see here. So we have completed 50 algorithms. So we are discussing around 120 algorithms or the all the important algorithms in the within the certain data structures, right? So we have completed 50. Still 70 more to go, right? 60 plus more to go. Basically, around 120 we are doing. So still we have around 70 this one algorithms to discuss, right? So this is one of the achievements. We have completed 50 algorithms. This is fine, right? So yep, we are done with the this one tree-based algorithms playlist. Also, we are done with the square root decomposition on trees algorithm as well, right? So before moving on with the next algorithm tomorrow, let me summarize whatever we have learned so far. Just give me a second here. So yeah, one more thing. It's ideal for the dynamic tree problems where both updates and queries are frequent, right? So now, next, as I've said, we'll be continuing with a graph-based algorithms, right? So we are done with the tree-based algorithms. Let's finish it off with this particular algorithm itself, tree-based algorithms. We are done with this particular playlist, right? Next, we'll be discussing on the graph-based algorithms. And again, I want to tell you that there are so many algorithms in the graph-based algorithms, man. There are so many algorithms. Let me read out loud. Just listen to this. We'll be going with the DFS, BFS. We'll be going with the Dijkstra's algorithm as well to find the shortest path, and we'll be going with the Bellman-Ford algorithm, Floyd-Warshall algorithm, Johnson's algorithm, Kruskal's algorithm. So this one, I wouldn't lie, I learned this one or I implemented this one correctly. So I would use this one. Uh, I try to implement this one in most of the contests and other stuff that is different. Mainly, I had learned this one during the college days, graph algorithms, right? Whether it may be DFS, BFS, Digista, Bellman-Ford algorithm, Floyd-Warshall algorithm, Johnson's algorithm, this one, Kruskal's algorithm, and also we'll be going with the Prim's algorithm, union find or the disjoint set union algorithm. So Tarjan's algorithm will be going with Tarjan's SCC algorithm. That's one of the important algorithm as well. Kosaraju's algorithm, SCC, that is also SCC, right? So Kahan's algorithm, this is one of the important or the famous algorithms on the topological sorting, right? So this is one of the things. So usually some of the problems from the LeetCode will be asked on the topological sort most of the times, right? So Hungarian algorithm will be discussing, Hopcraft Karp algorithm will be discussing, Edmond Karp algorithm will be discussing, Dinix algo also will be discussing, not to worry. Push relabel algorithm will be discussing, Eulerian path or the circuit algorithm will be discussing. Then finally, we'll be discussing on the this one, Hamiltonian path or cycle algorithm as well, right? So how many algorithms basically we discussed from this one? Almost 19 algorithms we'll be discussing from the graph. Within the trees, we have discussed around 14 algorithms. So within this one graph algorithm, we'll be discussing around this one 20 algorithms, almost 20, 19 algorithms we'll be discussing, right? Yep. After that, we'll be going with the DP. Basically, these graphs algorithm, we are left with very important algorithms, I would say. Graph algorithms we are left with. Number theory algorithms are also very important, right? So number theory algorithms, whether it may be Sieve of Eratosthenes, so Euclidean algorithms, so modular exponentiation inverse. Let's see that one later. Now, yep, as I've said, next we'll be discussing on the graph algorithms. Around 20 algorithms we'll be discussing basically, right? So now, yeah, we are done with the square root decomposition on the trees, and this is going to be the last algorithm, as I've said, within the tree-based algorithms playlist, right? For now, this is it. Thanks for watching, guys.